So today we're going to be covering an overview of patterns. In this particular discussion, we're going to talk about how experts typically look at the world a little differently from novices. When experts in almost any field, whether it be in martial arts or music or sports or dancing or whatnot, when they perform, they often look very effortless and very fluid. But a lot of times we tend to forget how much effort they put into making it look that way. So when I was a graduate student many years ago in California, I studied ballroom dancing. And I discovered very quickly on that the things I learned as a ballroom dancer didn't look anything like the pros do on, say, Dancing with the Stars, because I wasn't anywhere near as good as they were, even though I had some knowledge of very basic kinds of movements. One of the things that's really important to becoming an expert is continuous repetition and practice in order to become successful. Also, when I was an undergrad, I spent some time doing karate, and we spent a lot of time doing blocks and punches and kicks and so on. And once again, as a novice in martial arts, you learn the basic moves, but you're not really very good. And it's not until you start putting groups of blocks and punches and kicks together into katas or other forms that you get fluid enough to actually get a higher level belt, become considered to be more of an expert. Also crucially important in this whole thing is mentoring from other people who've done it before. So the people who taught the martial arts course that I took were black belts. The people who taught the dancing class I did were really experienced dancers. And so by modeling them, by having them break down complex things into more elementary individual parts and learning the different combinations and so on, makes a big difference in terms of getting to be a master yourself. Interestingly enough, at the heart of all of these different activities is understanding and mastering patterns. So if you think about music, when you learn to play music, you learn scales. When you learn to do martial arts, you do something similar to Karate Kid, wax on, wax off. You're doing these motions and repetitively repeating those things over and over again till you get good. Same thing with dancing, same things with athletics. You do all kinds of drills over and over and over again till you start to attain mastery. And patterns are crucially important to that. So let's go ahead and talk a little bit about patterns. Now, what I'm about to give you here is a very abbreviated discussion of patterns. If you want a more detailed discussion of patterns and you haven't already taken the CS251 course, where we cover this in great detail, consider taking it in the spring when I'll teach it next. It's probably too late to take it now for the fall. But there's also a set of videos you can watch online from the POSA Coursera course that will go over a lot of this material as well. Okay, so what we're going to talk about here is sort of understanding what patterns are and how they help to codify design experience so that people who are beginning in something can learn the best practices of those who have better or have more experience or have been successful. We're also going to talk about some of the common characteristics of patterns and the way in which people describe patterns. There's a couple of different ways to do it, and that's what we'll cover here. So what is a software pattern? A software pattern is essentially a solution or a reusable solution to a problem, a common problem, that arises within a particular context. And the context is crucially important to making sense of how patterns get applied. In our particular case, the context for a lot of what we'll be applying patterns for is the context of mobile applications. And if you recall, when we talked about frameworks a couple weeks ago, we talked about how Android had resource constraints. Android was trying to deal with battery issues. It was trying to deal with memory footprint issues. It was trying to deal with the fact that they wanted to leverage the Java installed base of programmers, touchscreen, interface-oriented, and so on and so forth. So those were some of the contexts. There are obviously many other contexts as well. There are contexts for aerospace, which have many of the same time constraints, often even more stringent time constraints than a phone does, but many times they'll have more resources. Typically, an airplane or a tank or a ship has its own power plant that's generating a lot more power than the batteries that you have in your handheld device or your tablet. Likewise, there's other domains where people are willing to throw lots and lots and lots of resources in order to be able to maximize performance, minimize latency, and so on. So the electronic trading or financial services domain, people throw a lot of resources of computing and networking into those problems and storage. Other domains, automotive, have all kinds of interesting characteristics. They have to go through fairly stringent safety evaluations and assessments, as do aerospace, especially commercial aerospace. Medical devices, same kind of thing. It's also important to realize that patterns don't just occur in the context of software technology. Has anybody here ever been to New Jersey before? Okay, a handful of you. So what do you call this funny thing that we have up here on the slide that says civil engineering? What is that called?
Cloverleaf.
So it's close to a cloverleaf. It's got a different name. Cloverleaf would be a generalization of what this thing is. This is what's typically called a jug handle in New Jersey. And the idea there is to allow people to turn left without having to block traffic that wants to go straight. And there's a whole pile of reasons why they do that kind of stuff. I won't go into all the details now, but if you take 251, you'll learn more about that. So what patterns do is they help to codify this expertise in a form that human beings, programmers, managers, architects, designers, and so on, are going to be able to understand and then apply to their daily work to make them more productive, make them more effective at building high-quality solutions. And there's certain things that patterns provide. One thing that patterns provide is a common way to name recurring design structures. And it may seem like a minor point, but think how important it is in our communication with other technologists if we all understand things like what's a for loop, or what's an if statement, or more interestingly, kinds of things that you'd have to think about is what's an operating system, what's a compiler. If you didn't know what those basic terms meant, you'd be very confused to try to communicate with each other. What's a linked list? What's a heap? What's a stack? What's an array? And so on. So that shared vocabulary is very important. For the particular example we're looking at here, you might have an arrangement of software that leads to something called the observer pattern, which essentially defines a one-to-many dependency between objects so that when one object changes its state, all of its dependent observers can automatically be notified, so they can do something about that. And we'll see that observers are used quite frequently throughout Android and other software environments. The pattern descriptions help to specify a number of things that make life easier for software developers, software designers, software programmers, software architects, software testers, and so on. One of the most important things that they do is they help to describe the commonly recurring roles and relationships between elements in a software design. And they do this by capturing key properties of classes and objects. Keep in mind, when I use the word class and object, I'm referring generally to the concepts of structures and methods, not specifically talking about classes in C++ or classes in Java or classes in Objective-C, although those are important. You can also do the same kinds of things we're talking about here if you program in a language like C, which doesn't have classes. You just have to arrange the software slightly differently. So for example, in the case of the observer pattern, there's common roles and relationships. There's the concept of a subject role, which kind of keeps track of the data and the data model. And then there are observer roles, and those are what are notified or updated when something changes in that model that's managed by the subject. There's also dependencies. As you can see here, the observers depend to some extent on changes to the state that's owned by the subject. So there's a relationship that is going on there that's a dependent relationship. Whenever something changes in the subject, the observers are automatically notified and updated to do something. There's interactions. Those interactions can take place by various means. They might take place by having the observer be notified by a method call when something changes that's managed by a database or a data table or something like that. But it also might be through message passing or telephone call. There's all kinds of different ways you can notify people and interact between the different roles and relationships in the observer pattern. And there's also a number of conventions that are important to understand. For example, in the classic observer pattern implementation, there's often only one thread of control. And so if an observer happens to block for an extended period of time during an update call, then it may starve out other observers. So you don't want to necessarily block for a much long period of time by convention. That might be a design rule that has to be followed by people who want to use this particular pattern correctly. Some other things that patterns help to do is they help to abstract away from concrete design elements. So when we think about the observer pattern, even though those things get reified or instantiated in the form of things like smartphones or tablets or desktops or servers or whatnot, there's nothing in the pattern that dedicates ourselves to one particular form factor versus another. You can have this pattern in all kinds of different form factors. You can have them applying in all kinds of different domains. You can have them applying with all kinds of different programming languages. There are observer implementations in Java, C++, C#, C, you name it. People have implemented different realizations of this pattern in many different ways. Patterns are also crucially important to distill and codify expert knowledge. For example, the observer pattern is actually a piece of a larger pattern which is called the model view controller pattern. And the model view controller pattern, you can trace its heritage back quite a ways. If you Google model view controller history, you'll find some discussions of the early work on this. But it really became popularized in the 70s and 80s with a lot of the early work that was done with Smalltalk. And that's the way that they developed the user interface environments with models, views, and controllers. And the observer is really a piece of that. It's sort of the model view portion of the model view controller pattern. Likewise, there have been people who have applied this pattern in wildly different domains than graphical user interfaces. So there was a toolkit called ToolTalk, which was part of the Sun distributed computing environment they had released in the late 80s. And ToolTalk allowed a pub-sub-like model to be used between various client-server entities in a networked environment. So the same pattern applied again, but it was found in a different guise. And yet it still distilled best practices and good insights that people could use for a variety of reasons. So the takeaway here is that patterns help to avoid reinventing the wheel. And if you're going to reinvent the wheel, at least make it round, or at least make it so that it doesn't go flat on a regular basis. So it helps you to build upon things that have been known to work. Let's talk a bit about some of the common characteristics of patterns, because there's quite a number of interesting things that patterns have. Once again, I'm not going to cover all different elements of patterns here, just enough so you kind of get a feeling for it with what we're going to be talking about in the context of Android. So a pattern describes both a thing and a process of producing things. So the thing is kind of the what. That's something that you might convey with some sort of interaction diagram, or it might be conveyed by a structure diagram, the kind of thing we just looked at with the observer pattern. And that helps you to understand what the high-level design is. It helps you understand what the roles and responsibilities are, who calls what when, and under what circumstances do certain things change, where do things vary, where are they common, that kind of stuff. So that's the thing part, or the what. But there's also the process part, which is a description of how to create these kinds of things. And when we talk a little bit later about different ways of documenting patterns in so-called pattern form, you'll see that there's a number of different ways of explaining the implementation steps, giving people guidance about what to do first, what to do next, what the potential variabilities there are at any given stage or phase along the way. If you take a look at this link here, you'll get an overview of a white paper written by a colleague of mine named Jim Copleen many years ago, probably 15 years ago or so, where he talks about the thing and the processness of patterns. And it's really cool. It's definitely worth taking a look at. Some other characteristics of patterns. We hinted at this earlier. Patterns are often, although not always, independent of particular programming languages. And this turns out to be a good thing for a whole bunch of different reasons. One of the things you will discover as you go through your career, no matter what programming language you start out with, chances are that will change multiple times throughout your career. In fact, it's getting to the point nowadays where most people don't write programs in a single language anymore, especially if you start integrating with databases or user interface environments and so on. You may be writing your business logic in C# or Java, but you're doing some SQL to describe selects and joins and other database operations. You might be programming with XML to describe the layout of your widgets, as we do in Android. So you have to be fluent with multiple languages. And one of the nice things about that is, just like learning to speak multiple human languages gives you a broader appreciation for the many ways of doing and being, so too does learning multiple programming languages give you a better sense of how to do a better job with doing and being of software development and trying to express problem solving via computation. And people who typically only know one language, just like in everyday life, often have a somewhat narrower view of the world. I once was on a vacation in Hawaii, and they said, what do you call a person who speaks 2 languages? That's bilingual. What do you call a person who speaks 3 languages? Trilingual. What do you call a person who speaks 1 language? An American. So we can all do better. I have to admit, I learned French in high school and college, but since I never had a chance to practice it, I've pretty much forgotten everything I knew. But the great thing about patterns are that they help to abstract away from the differences of programming languages and focus on this essential coreness of design and design relationships and design interactions and structure and dynamics. That's not to say that knowing a programming language isn't important. It's just that there's some things that transcend languages, and patterns are very useful to convey that. It's also worth pointing out in passing that patterns are often very useful to understand in particular language paradigms. So a lot of the patterns that we study in 251 here, the design patterns course, are patterns for object-oriented languages, or patterns where object-oriented languages where these patterns become most obviously useful. And that's because we tend to learn C++, Java, C#. if you were to program almost exclusively in functional programming languages like Scala or ML or so on, you would find that there are plenty of patterns there. They're just not quite the same patterns that you would find in the Gang of Four book, because the kinds of programming styles and best practices and so on that you do in those languages are different. And so the best practices, no surprise, are going to be different as well. Some other things that patterns do is they help to design or help to define microarchitectures. In other words, they describe these recurring design structures. And oftentimes these are captured in a way that typically has between, say, 2 to 4 roles and responsibilities and interactions between those roles and responsibilities. So here's our good friend the observer pattern. As you can see here, we have the observer part, which has some kind of abstract method called update, and we may inherit from that to make a concrete observer or a family of concrete observers that do different kinds of things. We have a subject that keeps track of state, keeps track of a list of observers, and it's got methods for doing things like attaching and detaching observers and then notifying the observers. And when you call notify, as you can see here, the notify method iterates through all the observers and calls their update method. Probably using the iterator pattern, by the way, just to show you how patterns can connect to each other. Here's an example of the observer pattern applied in Android. So it turns out that Android has lots of different instantiations of the observer pattern. Here's one of them. We'll look at another one in a second. And this particular example is something that's used with content providers. So content providers are typically an interface that's used to mediate access to data that's shared between multiple applications. And it's possible for you as an application developer to register an observer that will get called back when some of the data happens to change. And that way you don't have to write applications that repeatedly and inefficiently poll the database over and over again saying, has the value changed, has the value changed, has the value changed? Instead, you register some kind of observer, and then when the values change, there's some API calls you do to notify, and those things then call back using the Android framework to notify the various content observers that something's happened. And there's something called a content observable that's used much like the observer pattern has the subject. And the methods are slightly different. It's register observer, unregister observer, notify change, and so on. But the pattern is basically the same. Likewise, here's another example of using the observer pattern in Android. We'll talk about this later. Actually, we'll talk about both of these things later. This example is what uses so-called broadcast receivers. And broadcast receivers in Android are used to notify various interested parties when something changes. Say the battery is getting low in the phone, or you receive a new event from an SMS server, and you have to propagate that up to the handler of that event somewhere in the system. And we'll take a look at some of this stuff as we get a little further on into the course. So some of the names are different. You have a context instead of a subject. You have a broadcast receiver instead of an observer. You have methods like onReceive and register receiver and unregister receiver and send broadcast and so on. But the elements of the patterns still map nicely one-to-one to the elements in the Android mechanisms or frameworks that embody those patterns. By the way, there's a little bit of UML notation here. You can see here that we've used this sort of lasso-like syntax to say that the context plays the role of the subject in the observer pattern. And the broadcast receiver plays the role of the observer in the observer pattern, and so on and so forth. So that's a way of being able to show concretely the mapping between your design and a pattern that helps to document and justify that design. Really, really, really important to understand this as you start to work in teams in projects where you have to subject your designs or the designs of your colleagues to a close inspection to make sure they're doing the right things. Great way to get people's understanding at a much higher level in design review is to point to patterns that their designs embody. Of course, that assumes people understand the patterns, but if they don't understand the patterns, then you can go and point them to the literature to read more about that. Patterns are not concrete code. They're design artifacts. They're descriptions of things. They're codifications of recurring microarchitectures and so on. So in order to actually be useful, you have to turn them into something that's tangible. And the most common way to do that is either to take something off the shelf that implements the pattern, like elements you might find in Java or Android, and customize through inheritance or implementation those interfaces or classes. Or you may have to implement some of the stuff yourself. Some patterns are captured quite nicely in reusable artifacts that you can get off the shelf in the form of frameworks or component libraries. Other patterns are not something you get easily off the shelf. You have to understand how to assemble the pieces yourself, but they're still embodiments of those patterns. Here's a particular example of how we might implement a portion of the observer pattern in Java. This is not really Android-centric, it's just a piece of Java. So we have something that's called an event handler that extends the observer class, which is a part of Java, and it overrides the update method. And then you have another class that extends the observable class and implements the runnable interface, so it has a run method. And you can see here, under some circumstance, let's say you're listening to a set of I/O ports or something, or user interface events, under some set of circumstances, you're going to say, aha, something changed, I'd better go ahead and notify the observers. And that will cause the update methods of those observers to be called. And down here, we could kind of put all the pieces together. We could make ourselves an event source. We could make ourselves an event handler or multiple event handlers. We could add the event handlers to the event source, kick off a thread of control, and then go ahead and start running the application, and it would do its thing. So just a simple example of how you might realize this pattern in Java. Here's another implementation of that pattern. This time we're using C++. We're using ACE, which is the framework we've developed over many years to do various kinds of concurrent network programming using C++ on a wide variety of different platforms. Same pattern, just a different realization, but the same basic ideas. So illustrating how the various parts can fit together. Patterns are not methods. When you take the software engineering course or courses 278 and 279, you'll hopefully get a chance to be exposed to the software lifecycle, and you'll learn about various methods for developing software in teams, things like the rational unified process, or various agile methods like Scrum or Kanban and so on. And patterns are not actually methods. They are things that help make methods more effective. They capture best practices. There's patterns of doing agile development. There's patterns you can use to help develop software with rational unified process. You can, if you apply those processes and methods, you can use patterns to be more intentional about your designs and the implementations of those designs. So patterns, in some sense, are a little bit like accent flavor enhancer. You wouldn't really eat accent flavor enhancer, but you would sprinkle it on your food to make it taste better. It's not a food in itself. It's something that makes food arguably taste better. There are also patterns on lots of other things. Obviously, we're going to be focusing primarily on patterns for software, because that's what the course is about, and more specifically, patterns for mobile software and Android with Java. But be aware that there's also patterns for lots of other things. There's patterns for how you apply agile software development. There's patterns for how organizations are going to be more effective, be less Dilbert-esque, less dysfunctional, the patterns for that. There's actually a funny book called Dating Design Patterns to help people navigate complex dating situations, particularly important for engineers, right? So it makes people more effective in this environment. I actually saw the author of this book. She gave a talk at OOPSLA one time. It was just absolutely hilarious. She wrote the book in the Gang of Four style, and it's very humorous. So let's talk a little bit about different contents of patterns, of pattern descriptions. So first of all, it's important to distinguish between the pattern, which is sort of this metaphysical thing, and the description of the pattern, which is the way in which we come to understand the pattern. So the key reason that that's an important distinction is because there could be many different ways of describing something, each of which gives you a little bit different take on what that something is. Just like there's lots and lots of textbooks that will explain to you quicksort or binary search or other kinds of data structures and algorithms, because everybody has their own way of trying to do a better job of explaining it. So the same thing is true with patterns. We separate out the description of something, which might change or be done in different ways, from the thing itself. And everything is kind of a projection from that thing, people wrestling to describe in human language this abstract design entity. So one of the first things you have, of course, is the name of the pattern. So the name should be pithy, which means it should be concise, it should be memorable. It should be something like adapter, bridge, reactor, wrapper facade, flyweight, something when you hear it, you go, yeah, I know what that is. A little thing pops up in your head with some kind of image of that. You also should explain why you need to have this thing. What goals is it solving by using it? For example, if you recall the observer pattern, the goal is to define this one-to-many dependency between an object and things that depend on the object. So when the object's state change, everybody gets notified. That gives you a brief statement of what the thing's doing. You should also explain what problems are being solved by this pattern. Why would you ever apply it? So you might have things that may have different views, and you want to have a way to reconcile them in a consistent manner. Observer pattern, for example. So kind of explain when to apply the pattern. Give the solution, of course. You should say what to do. And the solution is typically characterized by some kind of visual realization with a UML diagram, often showing both the structure, maybe the dynamic parts as well as the structural parts. This is something where modern techniques with multimedia, with video, animations can really help to explain the inner workings of the software better. Just looking at a diagram often isn't very elucidating. So all patterns have those things. They typically have a name, the intent, a statement of the problem, and a solution. And then some pattern descriptions go into more detail. And these are often the ones that are most useful for programmers. So patterns often give you some examples of how to apply them. They're often written in your favorite language, C++ or Java or C# or Prolog or whatever you may want to use. Oftentimes there'll be a description of the steps to apply to make the pattern work for you. That's that process thing I was talking about. The structure is kind of the thing, and then the implementation guidance is kind of the process. How do you apply it? You also have good patterns describe the pros and cons of the pattern. What happens if you apply it? What are the good things that happen? What are the benefits? What are the liabilities? Very few decisions in computing come for free. There's almost always a trade-off between something or other. There's a trade-off between time and space. There's a trade-off between generality and understandability. And these things have to be documented carefully, because if they're not, you might think, oh, I can apply this pattern in this circumstance, only to find out it doesn't work very well in that particular context. To be a pattern, you need to have multiple uses, at least 3 independent, different known uses. Otherwise, it's really not a pattern. It's just a good idea. And there's nothing wrong with having a good idea, but it may not be a pattern. So known uses explain examples of where this pattern can be found, ideally in software written by someone other than you. Also, ideally, the patterns often arise in human environments, not just software environments. And so as we go through some of these things, we'll give some examples of human known uses. It's good to explain how this pattern relates to others. As we'll see in a second, patterns are not an island. They don't exist by themselves. They interoperate. They're very social. They like to interact. They're gregarious. So that's basically a summary of some of the issues related to patterns. Take a look at this link here for more information about different ways of documenting patterns. There's different so-called pattern forms. What I describe for you here is primarily the Gang of 4 form or the POSA form, but there are other forms as well for different purposes. OK, any questions about that? So just a quick overview. The next thing I want to do is give you a quick summary of the history and contents of some of the classic works on patterns. Now, if you took CS251, you're going to be familiar with some of this, but we didn't cover all of it. And we're going to cover a lot more of these patterns in this course, but I want you to have a good sense of what's out there. The key theme to come away with here is not so much to understand all the patterns I'm about to give you in Cliff Notes form in the next 5 minutes or so, but to understand that there's a vast literature out there on patterns, and so you have a good set of resources to go to if you want to learn more about this particular field of study. So the Gang of 4 book kind of came first from a book point of view. We'll talk more about that. The Pattern-Oriented Software Architecture Volume 1 book came sort of next, depending on how you count it, another major work. And then sometime later, the POSA 2 book, Pattern-Oriented Software Architecture Volume 2 book, came along. That was about 4 or 5 years after the other 2 books. I was the lead author on that book, but I had a role in reviewing and helping to shape the other books as well. Let me give you a quick history of this stuff. It's kind of cool. It goes back now well over 20 years. In the late 80s, Eric Gamma was a PhD student at the University of Zurich, and he was developing some user interface frameworks in C++ called ET++. Does anybody know what else Eric Gamma is famous for, out of curiosity? So he was one of the main people driving behind Eclipse, among many other things. He's done a lot of great work with the Eclipse Foundation. He also did a lot of work with Microsoft. He went to Microsoft recently. So he did a dissertation written in German, kind of hard for us to read if you don't speak German or read German, but he did some of the early work on software patterns. Then in the early 90s, he met some colleagues at some conferences, and they started to talk about how you might capture the type of thing he and his colleagues had been working on. They were largely doing user interface frameworks written in C++, in Smalltalk and other languages, and they started to think about how they might pool their work together. And then they published a paper in the 1993 timeframe that talked about software patterns, and that paper became the basis for their book, which was called Design Patterns: Elements of Reusable Object-Oriented Software, the Gang of Four book. I was a reviewer of that book when I was a grad student, and it really reshaped the way I thought about programming at the time. What was so cool about it was, while I was reviewing the book, I was also working on the Motorola Iridium project, which was the really exciting low Earth orbit space-based satellite constellation, which was one of the first uses of the Corba distributed object computing middleware at that scale. And what was cool is I was learning Corba, and I was seeing all these patterns that were in the Corba implementation, and they were directly from the Gang of Four book. There were adapters and chain of responsibility and bridges and strategies and all these kinds of things. But the Gang of Four book had not been published yet. So there could have been no possible way that the people who were writing that Corba implementation, Orbix, could have known of that book's existence. But they were still using the same patterns. And that helped to teach me two important things. Good developers will come up with common solutions because it's the right thing to do. And what was also cool was that the Gang of Four book was all motivated by people doing user interface software, whereas the book from the Orbix software was all being done by people who were doing distributed object computing. Very different seeming domain, yet the patterns were quite similar. In 1994, in August, was the first Pattern Languages of Programming Conference, or PLOP conference, kind of a funny name. And a bunch of us got together at a really interesting place called Allerton Park, which is near University of Illinois, Urbana-Champaign. And a book came out of that. I was the editor, co-editor of that book. In 1996, the next big volume of pattern collections, the so-called POSA 1 book, was published. We'll be talking in a second about some of the patterns that relate to Android there. 2000 timeframe, I published a book with my colleagues who'd done POSA 1 called POSA 2. A lot of patterns we're going to be covering are in that book. And we worked on this stuff for years. This stuff didn't just fall off the turnip truck. People have thought a lot about this. They built software. They stepped back and tried to generalize from their experiences. They kicked ideas off of other people. People reviewed the patterns, gave them feedback. We got rid of the stuff that was goofy and so on. And then over the years, a bunch more POSA books were published, some of which I was involved with, some of which I wasn't. But the point is that there's lots of really cool material in this space now. So real quick, the Gang of Four book has 23 patterns. You can break them down all kinds of interesting ways. In the interest of time, I'll go through this very quickly. There are two different ways of looking at the Gang of Four patterns: purpose and scope. Purpose reflects what the pattern does. And there's three different types of purposes. There's creational patterns that abstract the process of making something. There's structural patterns that define how you can combine different classes and objects to form bigger structures. And there's so-called behavioral patterns that deal with the interactions between classes and objects in various canonicalized ways. There's also the scope, which is, do you apply the patterns to the classes and/or do you apply them to the objects? And based on that rough categorization, the patterns split up into these different categories. The Gang of Four patterns don't deal with concurrency and networking a whole lot, but they're very widely used for all kinds of things, including implementations of frameworks that themselves have a lot of concurrency and networking embodied in them. So we're going to see all these patterns I've checked. We'll see examples of these in Android at various points along the way in our discussions in this class. And there's other things, if you look long enough, you'll find other examples of patterns in Android that are not the ones I've checked. So the people who did Java, the people who did Android, were very, very up to speed on the Gang of Four patterns, and it influences a lot of what they do. If you want to take a look, there's a nice link here that gives you a bunch of examples of Gang of Four patterns applied to Java. So it's kind of fun to see where you can see other examples of these patterns in Java. The POSA 1 patterns, there were 17 patterns in that book, or 16 patterns in that book. Let's see, I think there's 16 patterns in that book. And they split them into two sections: architectural patterns and design patterns. The architectural patterns really deal with these fundamental arrangements of the core architecture, the core structure of the software. And the design patterns basically deal with how do you take smaller pieces of the system and arrange it in various ways. Many, many of the POSA patterns relate to concurrency and networking and distribution and so on. And we're going to talk about a whole pile of them in this class. We're going to talk about proxy, we're going to talk about command processor, we're going to talk about publisher-subscriber, we're going to talk about the model view controller, we just mentioned that. We're going to talk about broker, reflection. All these things are something you see a lot of in Android in various ways. Then the third and final book, the POSA 2 patterns. There were 4 major categories, 17 patterns. service access and configuration patterns, patterns for how you organize software and give access to services, patterns for dealing with different kinds of event handling, patterns for dealing with different kinds of concurrency relationships, and patterns dealing with different kinds of synchronization and interaction type relationships. And as you can see here, we're going to talk about many of the POSIT 2 patterns in the context of Android as well. And when you start looking into the internals of a lot of the implementation parts of Android frameworks and middleware and communication mechanisms, you'll see these patterns galore. They're used all over the place. It's pretty cool. OK, so to summarize, the Gang of Four book and the POSIT books, the early POSIT books talk largely about pattern collections, which are groups of standalone patterns rather than pattern relationships. Standalone patterns really give you point solutions. They talk about bridge, they talk about adapter, they talk about proxy, they talk about these things in kind of isolation. And in some sense, they provide you a vocabulary for talking about design, which is great. But in reality, any significant design actually includes many patterns that work together. And so as we go through the Android examples, I'll show you places where patterns arise onesie-twosie, but what's much more important is to see how they all work together. And you'll see that there's all kinds of ways of combining patterns into pattern compounds and pattern sequences and pattern languages and so on and so forth. In practice, a standalone pattern is very unusual. You very rarely see one pattern by itself. They're mostly there just for teaching purposes. OK, so that's the end of patterns. Like I said, kind of an intentionally short description just to get everybody up to speed. If you have any questions as we go through the later material about patterns, let me know. I'll be happy to give you more detail. From now on, we're going to talk about specific patterns in specific contexts.